Class, good evening. Now, today I am going to start with 1 or injective function. First, let me make very clear what are functions. Now, you know a relation R from a set A to the set B is a subset of A cross B. Now, in 11th class also, I cleared you this relation is a function. Relation R is a function. If for every element of A, there is a unique element of B. So I can say relation is a function. We define f from A to B if f correspond every element of A to unique element of B. For example, I have the set A and B as 1, 2, 3. Now I define relation R as say 1, 2, 2, 3, 3, 1. Now this relation is a function because for every A we have a unique image. So it's a function. Whereas if I define say another relation, say R2 as 1, 1, 1, 2, 1, 3. So that's not a function because one has got many images. So it's not a function. Now, today I will come up with the type of functions that is 1, 1 or injective function. We say 1, 1 function, or we say same as injective function. Now, I will define what is a 1, 1 function. A function f from A to B is said to be 1, 1 if for all x1 and x2 in A and f of x1 equals to f of x2 implies x1 equals to x2. Or you can write, so we can say f is 1, 1, or x1 not equals to x2 implies f of x1 is not equals to f of x2. See, in class 11th you have done, if p implies q is true, if p implies q is true, then negation q implies negation p is also true. So in this case, we can have either this definition or this definition. If in turn, in this case, you have f of x1 equals to f of x2 gives x1 not equals to x2, function is not 1, 1. Or x1 is not equals to x2 gives f of x1 equals to f of x2, function is not 1, 1. So these are the cases of not 1, 1. So these are the example of not 1, 1 case. Now hope it's clear. I am again saying a function f from A to B is set to 1, 1 if distinct elements have distinct images. Like this also you can learn. It's again known as injective function. So Let me come up with some examples there of 1 function. I define f from R to R as fx equals to 2x plus 3. Show that f is 1, 1. Now I will apply both the methods, equals to and not equals to both also. So you write let x1 and x2 belongs to R, that is codomain. See, here R are both, this one also, this one also. So I will take from R only, this R, codomain. So you will write f of x1 equals to f of x2. Well, this will becomes 2x1 plus 3 equals to 2x2 plus 3. This means that x1 equals to x2. This means f is 1, 1. Or when it's not equal, you have x1 not equals to x2 implies 2x1 not equals to 2x2 implies 2x1 plus 3 is not equals to 2x2 plus 3 implies f of x1 is not equals to f of x2 implies f is 1, 1. In exams, you can use both of the methods, no problem as such. So this is the case where function f is 1, 1. Okay. The case where function f is not 1, 1, you have to show by example usually, or some ways you can also show by the proper method and explanation, but after that one step you will contradict that, right? I define function f from R to R as fx equals to x square. Is f 1, 1? Answer is no. Now you will write let x1 and x2 belongs to R, that is codomain. Now you have f of x1 equals to f of x2 implies x1 square equals to x2 square. This will give you x1 equals to plus minus x2. Now as x1 equals to x2, but x1 equals to minus x2 also, so f is not 1, 1. Though example is not required, either you can take examples, I can give that also. Let minus 1 and 1 belongs to R. Now, minus 1 is not equals to 1, but f of minus 1 is 1 and same as f of 1. So you have f of minus 1 equals to f of 1. So f is not 1, 1. So if it is not 1, 1, sometimes you give the example, most of the times rather. Sometimes you can illustrate like this also. So this function is not 1, 1. Now, in the same way, if you define f from R to R as, say, modulus function, is this function 1, 1? No, you will write like same. Let x1 and x2 belongs to R, and that is codomain. Now f of x1 equals to f of x2. This means mod of x1 equals to mod of x2. This means x1 equals to plus minus x2. Again minus is coming, so f is not 1, 1. In the same way, class, if I define f from R to R as fx equals to bracket x, the greatest integer function, show that f is not 1, 1. Now you can take actual example there to show that it's not 1, 1. Let you can say 1.1 and 1.2 belongs to R, that is codomain. Now 1.1 is not equals to 1.2, but f of 1.1 is 1, f of 1.2 is 1 because of the greatest integer. As bracket of 1.1 is 1, bracket of 1.2 is 1. So f of 1.1 is f of 1.2. So f is not 1, 1. So these are the cases, examples where I have shown that function is 1, 1 and the cases where function is not 1, 1. Now, another question, define f from R to R as fx equals to sin x. Is f 1, 1? So, you can say mostly answer is no, because let 0 and pi belongs to R, codomain. Sorry, it's domain. I'm very sorry, class. Everywhere you should write domain. Codomain is this one, domain is this. So it's codomain. Class, please correct all this. In previous cases, it's written domain. Where I has written codomain, you make it domain. Let 0 and pi belongs to R. Now, f of 0 equals to f of pi. F of 0 equals to f of pi. Or you can say that 0 is not equals to pi, but f of 0 equals to sine 0, f of pi is sine pi. Both are 0. So you have f of 0 equals to f of pi. Also, f of 0 equals to f of pi gives sine 0 equals to sine pi, but 0 is not equals to pi. So f is not 1, 1. In the same way, define f from n to n as fx equals to 1 by x. Is f 1, 1? You will write let x1 and x2 belongs to n, that is domain. So you have x1 f of x1 equals to f of x2. This means 1 upon x1 equals to 1 upon x2. This gives x1 equals to x2. This means f is 1, 1. So here f is 1, 1. Whether I take up the same question as say f from n to n defined by fx equals to x square. Is f 1, 1? Answer is yes, because here we are from n to n. Now, if I take f of x1 equals to f of x2, being in n, I can't take minus x2. So x1 square equals to x2 square, and so x1 equals to x2, and so f is 1, 1. So these are some of the examples of 1, 1 case. Now some more examples of 1, 1 cases. Define f from R to R as fx equals to x cube. Is f 1, 1? Answer is yes, but how to write it out? You'll write let x and y belongs to R, that is domain. Now, f of x equals to f of y. This means x cube equals to y cube. Now, at once you write x equals to y, but you have to prove it how x equals to y. Now, this means x cube minus y cube equals to 0. This means that x minus y into x square plus xy plus y square equals to 0. This means either x minus y equals to 0 or x square plus xy plus y square equals to 0. So I will prove that this is actually not equals to 0, because this can be written as x square plus 2 into x into y by 2 plus y square by 4 plus 3y square by 4. So this is x plus y by 2 square plus root 3y by 2 whole square. So both are positive, both are square, and If they are equals to 0, that means this whole is equals to 0, but since they are square, so square usually is greater than or equals to 0. So since it's greater than 0, I can't say always that it's equals to 0. It's maybe greater than 0 also. But here you have x equals to y. So you will take the separate case, x minus y equals to 0. And so x equals to y. So it's 1, 1. So you have to present your answer exactly like this way. Here you have only case that this will be equals to 0 only, and here it's greater than 0 also. So you may now take this case, right? Okay, now the last example, I define f from say minus 1 to 1 to minus pi by 2 to pi by 2. Or you should say this, f from minus pi by 2 to pi by 2 to minus 1 to 1 as fx equals to sin x. Is f 1, 1? Answer is yes. See, here domain and range are being changed. Minus pi by 2 to pi by 2, minus 1 to 1. So you write let x1 and x2 belongs to minus pi by 2 to pi by 2. Now you have f of x1 equals to f of x2. Now this means that sine of x1 equals to sine of x2. Now sine of x1 equals to sine of x2. This means that sine of x1 minus sine of x2 equals to 0. So that means 2 cos of x1 plus x2 by 2 sine of x1 minus x2 by 2 equals to 0. This means that sine of x1 minus x2 by 2 equals to 0. Cos of x1 plus x2 by 2 equals to 0. Now this will give you x1 equals to x2. This will give you x1 plus x2 equals to by 2 equals to pi by 2. So it's pi. So we don't require this. So we require this only. That means in one case it's coming x1 equals to x2. So we can say f is 1. So I discussed many examples of 1, 1. Hope it's clear to you. Any doubts, you can ask me. Thank you very much.